Yes. Is my screen visible? Can you see the PPT?
Yes.
Yes, sir.
Yes, sir.
Okay, very good. So as you all know, the last topic of our course is the aromaticity. So these are the things we'll learn in this last week. So at the beginning, we'll learn about the concept of aromaticity and what are the criterias, and based on the structural and electronic, the energy criteria for aromaticity. And then we learn about the Huckel's rule. So Professor Huckel, he defined the rule to be an aromatic compound. We'll learn about that. And at the end, we'll learn about what is the anti-aromaticity, the opposite of aromaticity. And of course, these things we'll learn from simplified molecules. And then we'll also, with that experience and knowledge, we'll just extend that in monocyclic hydrocarbons and also some more complex molecules. Okay. And I really don't want to go to in very very depth, because it's a basic course. So I think we can cover in 2 classes, and we have 3 classes this week. So I've decided that tomorrow's class will not be there. So today I will teach and try to cover this part. I think I can easily cover this part today, the first 2 things up to Huckel's rule. And then in the last part, we'll discuss on Friday. Okay. And instead of having class tomorrow, so I have given one assignment, probably already, I believe some of you already noticed in WeLearn, I have given an assignment from the thing that we learned today. Okay. So we learn something today, and applying this thing, you have to solve this assignment, you have to do, and you have to submit within a week. So that's the thing. So let's start. First, as you know, when we learned stereochemistry at the beginning, I gave you some brief history of stereochemistry. Here is the same. Little bit of history. And the thing is, whenever we hear the word aromaticity, the very first compound comes in our mind is definitely benzene, right? So I'm sure if I ask you to give an example of an aromatic compound, 99, more than 90% of you will tell me benzene name, and 100% people will say something, if not benzene, some derivative of benzene like toluene or so. Yeah. So this benzene is special and is really linked with aromaticity, the term aromaticity. Now the thing is, benzene was first isolated by Michael Faraday. Faraday had so many contributions. This is probably also one of those small contribution, but he have done many other great things. But basically, he invented benzene, or not, should not say invented, first isolated. Benzene was there already. He isolated in, you see, it's 1825, quite early. But at the time, the structure and all these things was not known. And then there was a debate, what's the structure of benzene. Some people said it's a triene. Some people said it's not a cyclic compound, it's a acyclic compound, because you can't see a molecule, right? So you can just see benzene, a colorless liquid, and it's not easy with the technique that were available at that time. But these chemists or scientists were really great. And then first, the Michael Friedrich Kekule, he thought that benzene is cyclic, definitely, and having 3 double bonds, but these 3 double bonds are not localized. What I mean, he thought that if you see, this is one of the structure of benzene, so it's having 3 double bonds here. So Kekule said that these 2 structures are equivalent and equilibrating very fast. Okay, so that was his statement. And why he made this statement, it was based on one experiment. So what he did, so he was working on the bromination of benzene, and then when he prepared this dibromobenzene from benzene, and if you just write down the structure of dibromobenzene with different permutation combination with different regioisomers, just keeping one benzene fixed, if you just put the other benzene in different positions, so one two dibromo, one three dibromo, and one four dibromo. If you draw that, so you will see you will get four structures. Is there any message came or just a moment?
Just now the slide changed. It wasn't visible at first, so that's
Is it?
why.
Okay, I don't know why. So now it's changed. In the
Yes,
PowerPoint mode, it's not changing
just
or
now.
what? I changed the slide. Is it changing now?
We are
No, sir.
seeing slide 2, sir, now.
Slide two. Okay, not changing. I don't know why. But then what I'll do, I will just skip the slides here mode, just like this. Although it will be a little bit smaller. Okay, it's fine, no? I will tell the things. You don't really need to read the text. All right. Text probably a little bit smaller. And what I will do, I will share this file in a PDF format. So whatever the study material, whatever is in that PPT, I will share you with a in a PDF file. All right. So please learn that. But now just hear what I'm saying, and then you try to get the concept. Sometimes it happening. It's also happened. I don't know. I have to solve this problem when I'm in Google Meet. Whenever I'm going to the slideshow mode, it's not changing the slide. So I would rather to go to slide share mode. I will just like this normal view. So these are the structures of benzene. So Kekule. So he was preparing this dibromobenzene, as I said, one two dibromo, one three dibromo, and one four dibromo. And if you just look at these structures, you'll see, and if you just imagine that these double bonds are fixed, okay, not like this, that it's not equilibrating between these two structures. These are fixed, okay. Now you see, let's start from the right hand side, then we'll go to the left hand side. If you see this 1,4 dibromo, the carbon which is attached with this bromine, you see this carbon is having one carbon carbon double bond here this side and one carbon carbon single bond this side. Okay, same here, this carbon which is attached to this bromine, I'll make it a little bit bigger. This is also having one carbon carbon double bond this side and one carbon carbon single bond this side. Okay, so if you sum up what are the bonds around this carbon which is attached to the bromines, so that this carbon having these two carbons having two times double bond, two times single bond. Okay, here if you go here, you'll find the same. This is double bond here, single bond here, double bond here, single bond here. Okay. So I have two times double bond, two times single bond. But if you go there, you see in this particular structure, these two particular structure, so these here in between these two carbon carbon bonds, where the carbon bromine is there, is linked with a common double bond. Okay, a common double bond. And here if you go there, these two where this carbon carbon bromine bonds are attached, here these two are connected with a common single bond. Okay. So if we consider that this double bond, these two structures are not equilibrating, then these two compounds should be two different compounds. So I repeat, in this case, the carbon-carbon bond where the carbon bromine is attached, in between there is a single bond, but here it's a double bond. Okay, so that's why these two should be different. Where this is a 1 2, but with this 1 3 and 1 4, whatever you do, if you draw the other structure also, you will get the same. Okay, you will get the same. You can try at home. But for 1, 1, 2, it's possible to get two different compounds theoretically. But when Kekule did the experiment, he found only three types of compound for 1, 1, 2, 1, 3, and 1, 4. That means for 1, 2, whatever he is thinking that these two should supposed to give two different compounds, actually these two are not giving two different compounds, rather is giving a single compound. That means these two structures are changing or interconverting with each other very fast. Okay. So based on this experiment, he assumed that this benzene ring is actually these three double bonds are not static, rather is interconverting with the other structure. Okay. And he said that these two are equilibrating. So this equivalent structure, equivalent this equilibrium thing. So rather later on we'll learn whether it's correct or not. But just as a invention of a theory at the beginning, just to propose for the first time, it was a great thing, right? And later on, so these things, based on some experiment, and then he gave the theory, and later on there was another experiment by this another scientist. So he really proved that the benzene structure is cyclic. So what he did hydrogenation of benzene and got cyclohexane. Cyclohexane structure was known already at that time. So he proved that from a cyclic structure, if you do hydrogenation means you are just converting the double bonds to a single bond. If the starting material benzene itself is not cyclic, it's not possible to get the product as cyclic. So based on that, he proposed or kind of proved that benzene is a cyclic structure. But debate were going on. So for any theory, it's in science, it's always there are opinion. It's not only in science, in everywhere. There people are fighting with different opinion. With benzene, there was a lot of fight, different opinion, a lot of debate, and all these things. And finally, it came to an end in 1930 when the modern technique of X-ray came. And X-ray is something, as you know, in a solid state. Now there are in liquid state also there is X-ray possible. So at the time it was in solid at low temperature. From X-ray you can really see the molecules, so you can get basically the diffraction from the crystals, and from this X-ray electron diffraction. So people came to know about the exact structure of benzene, and that was the end of the debate. But now you think, so this was the brief history. Now what are our topic of discussion is the aromaticity. So what gives benzene aromaticity? The thing is, the criteria or the property that gives benzene aromaticity is the resonance, a special kind of resonance. And this resonance probably you have already know about resonance. That resonance is nothing but is the contributing structure that shown in the double headed arrow, which are in Kekule. In the previous slide, I have shown I mentioned that Kekule showed that two benzene structures are in equilibrium. Okay, but later on scientists proposed, and now it's well accepted, that these resonance structures, these are not in equilibrium. Right here, as I have shown here, that this just notice this arrow. This is a double-headed arrow. It's not an equilibrium sign. Okay, so that means these structures are not really in equilibrium. The real structure is in between these two. Okay, something in between these two, kind of average of these two, and the resonance is where these electrons of the loosely bound electron or the pi electrons or non-bonding electrons are delocalized among the pi orbitals. Okay, so that's the resonance thing. And before learning about more details of resonance, you have to learn or you have to understand the meaning of delocalization. So from the previous slide, you have already understood that resonance is something linked with delocalization. As I said, the loosely bound that the pi electrons or non-bonding electrons are moving around the pi orbital or the p orbital of the molecule. That means these electrons are delocalized over these available orbitals. Okay. So if I read from here, the delocalization of electrons and resonance can be significantly affected by the properties of the chemical compounds. Okay. And there are some rules. Okay? Rules, as I said, to learn the aromaticity first, you have to learn about the resonance, and in other words you have to learn or about the delocalization. And for this resonance or delocalization, there are certain rules that you need to understand. The thing is, the rules for these drawing resonance structures, only electrons with pi electrons or non-bonding electrons in the molecular positions, that the pi electrons and non-bonding electrons can move. And the main structures, the nucleus or the sigma structure of the molecule, that should remain static. Okay, you should not touch the sigma structure of the molecule, that should be there. Only the pi electron or non-bonding electron can move. This is the one thing. The net charge, the second point is the net charge in each of the contributing structures should be the same. So just by doing a resonance structure, just by drawing a resonance structure, you can't really generate new charge. The overall charge must be same. What I mean, suppose it's a benzene molecule, it's a neutral molecule. Just by drawing a new structure, you can't make a negative benzene or a positive benzene. Okay. So definitely you can make local charges in one part of the molecule positive, one part of the molecule negative. Okay, so that you can do, but the overall charge should remain the same. Okay, if you sum up these charges, you must get the same charge that we started with. Okay? So if you use the neutral molecule, you can do something with a positive here, negative here. So overall, if you add plus minus, will cancel out, and then you'll get a neutral atom. So this should be there, but you can't really generate a new charge. Okay? So this is with example we'll see. And now there are some also you need to learn about the stability of different compounds. So if just with a benzene you can draw hundreds of structures just by changing here and there, but not necessarily all the structures will be having same stability. Definitely if you draw some abstract hypothetical structure, that it theoretically is possible, but the contribution in the resonance structure in the resonance hybrid, it will be less. Okay? So how to predict the stability of different resonance hybrid? If there is a incomplete octet, or in other words, in suppose you draw three different structures of just by moving the pi electrons and non-bonding electrons. In one case, the octet is filled. All the octet of all the atoms are filled. So that structure will have higher contribution. In other structure, suppose the octet is not filled. That means, so always try to fill the octet. Then in whatever structure the octet will be filled, that structure will be more stable. And if octet is not filled, that will be less stable. And the negative charge of the most electronegative atom and positive charge on electropositive atom, that is quite obvious just by moving these electrons. So if you put a negative charge in one structure, negative charge like in an electronegative atom like oxygen, fluorine, or nitrogen like this, then that structure definitely should be more stable. And if you give positive charge on more electropositive like carbon or silicon or something like this, so that would be more stable. If you do the opposite thing, that would be then those structures will be less stable. And the last So let's discuss with these two examples. So one is this carboxylic acid resonance structures and this carboxylate anions. Let's move a little bigger. There we go. You see here. So what we did, because it's having a non-bonded electron here, this oxygen, if you push there, you will get a plus here, minus here. Definitely it's a neutral molecule. If you add plus minus, it's also get a neutral molecule. But so what's happening here, you generate a positive charge on an electronegative atom. So compared to this normal structure, this resonance hybrid, the number B will be less stable, definitely. But now if you come here for carboxylate anion, which is already starting with a mono anion, to push this electron here, and then this make a double bond here, and then this negative charge will move to another oxygen. If see by doing so, of course, this is starting with -1. Here also we get a -1, but there is no positive charge on any of these oxygen, and we are getting two equivalent structures. Okay. So when we get this kind of equivalent structures, so then it gives really stability in the system. So that means these electrons are really uniformly distributed over this pi system. Okay. But in this case, in acid here, although the overall charge is neutral, but just by putting this resonance, we made an unstable structure. Okay. So these are the things. So let's move forward. So what really matters? So why this? Why you are learning this? Why it really matters? The thing is, the greater the predicted stability of the resonance contributor, the more is the contributes to the resonance hybrid. That we already discussed. That in carboxylate acid, we have seen the left hand side where is the normal structure is there, that is more stable. The right hand side where the oxygen is positive, of course that's possible theoretically, but the contribution in the resonance hybrid, definitely it will be less. And the number two, the greater is the number of relatively stable resonance contributors, the greater is the resonance energy. So definitely, so if you, it's possible that there are 5 structures and then really 4 of those having low energy. It's following that rules that I have mentioned there, filling octet, and then there's no negative positive charge on electronegative atoms, rather a negative charge on electronegative atoms, and so these things so are having low energy contributors. Okay, so then overall the resonance energy will be more, so that's quite obvious. And the second point is, what is the advantage having delocalization? Delocalization means possibility of new orbital overlap. So this is coming into, now it's coming to molecular orbitals. Okay, we are moving our discussion to other molecular orbitals. So delocalization means the possibility of new orbital overlaps. Okay, so if it's a static electron in a p orbital, okay, so that means it's there is no overlap. But if this orbital interact with a neighboring orbital and it's a bonding situation, it's a make a new molecular orbital, then only these electrons can move around. Okay, so then only the delocalization is possible. So in other words, if delocalization is happening, that means there is a bonding situation or new orbital overlap happened between different atoms. It's already bridge is ready, that's why electron is moving around. Okay, and whenever there is a overlap between orbitals and making new sets of orbitals, and electron gets the opportunity to going to lower energy orbitals, the system gets the stability. We'll see this MO thing later on in our discussion. So let's move forward. Okay, so now these are the kind of theory on delocalization and resonance are also, and now we'll move to the discussion again to benzene. We started with benzene, definitely, with the history of benzene in aromaticity and Kekule's structure. But now the thing is, why people thought that benzene is aromatic and having more stability. Okay, so Kekule, of course, as I said, with the this dibromo thing, he had some doubt why it's not giving four structure rather than it's giving three structures. And so that means there is must be this three double bonds are not static. So in between two structures, and there is an average between these two structures are quickly interconverting. But can we prove experimentally that really that this benzene, which is having three double bonds, these are not really a cyclooctatriene? Is it? It's really not a cyclooctatriene. So people prove that there is a very good, nice technique to prove that the benzene is not a normal cyclooctatriene. So the technique is, or experiment is, hydrogenation of benzene, heat of hydrogenation of benzene. So here's the experiment. I will rather discussing the text here. Rather, I prefer to show you the diagram, and oops, and I will mention you the text. So here is the experiment. So experiment is, you take a molecule here, right, and you do hydrogenation. So you put the you react with hydrogen, and whatever energy is releasing, okay, whatever energy is releasing, you will calculate that energy. Okay. So suppose this is just cyclohexene, the six-membered ring with a single double bond. Okay. Cyclohexene. And now, if we just react this double bond with hydrogen, we'll make two carbon-hydrogen bonds, and then we'll form cyclohexane, absolutely saturated molecule. Now, it is already known that the heat of hydrogenation of the cyclohexene is 28.6 kilocalorie per mole. Okay. So that means a double bond, if we hydrogenate, you will get the release of heat will be 28.6 kilocalorie per mole. Now, if just following this, if benzene is a triene, cyclohexatriene, then the heat of hydrogenation should be 3 times of this. Okay. So 28.6 into 3. So whatever value is there, so the heat of hydrogenation should be that much. Okay. So this is the right hand side is the theoretical value. So considering that cyclohexatriene as a benzene, as you can see here, it's a very distorted structure is because it's a hypothetical structure. So now you know that carbon-carbon double bond and carbon-carbon single bond distance is not the same. Carbon-carbon single bond, of course, is a bit longer, and carbon-carbon double bond is shorter because it's doubly binded, right? So if it's benzene is cyclohexatriene, then this carbon-carbon double bond should be shorter and carbon-carbon single bond should be longer. The structure should have been like this. And the heat of hydrogenation should be, if you just multiply this with 3, so you will get 85.8 kilocalorie per mole. You're supposed to get this much theoretically. But in reality, when people did the experiment with benzene with and hydrogen, they got only 49.8 kilocalorie per mole of heat. Okay, this much heat is released actually. Then what about the rest? So theoretically you're supposed to get 85.8, but reality in experimentally you got only 49.8. So that means benzene, the cyclohexatriene, whatever the energy level here. So at this point I must mention that this absolutely saturated one, the cyclohexane, is lowest energy. Okay, because it's having more number of sigma bond, more number of sigma bonds is having. That's why anything having normally more number of sigma bonds are more stable. So if you see the bond energy, if you just Google it in bond energies, you will see that carbon-carbon bond energy is more than the carbon-carbon double bond energy. What I mean that one carbon-carbon double bond means what? So there is a carbon-carbon single bond and it's a double bond. So the second bond energy, the pi bond energy is always less. Okay, so pi overlaps, the sigma overlaps are really face to face. So that there is a sigma bonds are always more stable. Pi bonds are parallel and then having the electrons there. So there is no real kind of overlap. Of course, this mixing there, but sigma bonds are always more stable. Hmm. So the cyclohexane, where the all sigma bonds are always more stable compared to the is unsaturated derivatives. Okay, so cyclohexene with only one double bonds here. If you it's not here cyclohexadiene, it's relatively more energy. Cyclohexatriene, which is a hypothetical molecule, is supposed to be higher. So always you are going down. So now for benzene, there is a heat of energy. It's when the people have done experimentally, there is a the amount of heat released was less than expected. So that means benzene was already in a more stable position. Benzene was already in a more stable position compared to cyclohexatriene. Okay, so cyclohexatriene was here and benzene was here. So it was already in bit stable position. So this much energy is actually 36 kilocalorie per mole. That is the aromatic energy of benzene. Okay. So because of this aromaticity, benzene got more stability than cyclohexatriene. Okay, and that much energy, or already benzene released that energy previously. Okay, that's why it's already in lower energy, and when you did this hydrogenation, it get only this much energy back, heat of energy. So that's this 36 kilocalorie is the resonance energy. All right, this was kind of experimentally done, and then let's go back to the theory of aromaticity. So what makes one compound aromatic? What are the criteria? Okay. So these criteria was first proposed by Professor Huckel. So that's called the Huckel's rule. In next slide, we'll see all the rules kind of in more details. But just to mention, that what are the criterias. The Huckel, although this one thing to mention, this aromatic compounds we are discussing about the electronic and cyclic these structures, but the name itself is nothing related to this Huckel's rule or so, because name this aromatic compound is really coming from I don't know from when, so very beginning, or and at that time the electronic structure and all these things, of course, it was not known. So rather the properties of the molecule that triggered or give force people to give the name. So this in ancient ages, or when these people collect nicely smelled compounds with aroma, and most of these compounds are aromatic. Okay, so from the name aromaticity actually came from this aroma, which gives good smell. Okay. It's nothing related to the structure. Anyway, so now coming back to this Huckel's rule, this is a German chemist. He was Professor Huckel. Germany has a lot of contribution in chemistry. This is one of these. The Huckel, he predicted, just by analyzing different structures, he predicted that to be aromatic, one compound must be having odd number of pair of pi electrons, odd pair of pi electrons. Okay, like 1 pair, 3 pairs, 5 pairs, 7 pairs, not electron, pair of electrons, that he predicted, and later on he put in a rule. It's a in a formula. It's called 4n plus 2. So we'll go to the next slide where I've shown this in more details. That in 1931, actually, Huckel predicted this. He said that to be aromatic, one molecule must have 4n plus 2 pi electrons. Okay? And this n is integers. It can be 0, 1, 2, 3, 4. So if you consider n equal to 0, so then you can see this is 2 electrons. That means one pair of electron. If it's 1, then it's 6. like this, and so 2, 6, 10 like this of electrons it must need. But that's not the only criteria. That molecule must be planar. Okay, so that molecule must be planar. If the molecule is not planar, then this delocalization will not happen. Okay, so one thing you need to learn, that for delocalization, one molecule, one this pi system must have been planar, because if the pi, these p orbitals, if not parallel to each other, then there cannot be any overlap. So if it's not in the same plane, the sigma structure is not in the same plane, then this resonance will not happen, this delocalization will not happen. So then that molecule cannot get aromaticity. Okay, so this should have 4n plus 2 pi electrons and must be planar and must be cyclic. Okay, these are the three criteria: it must be cyclic, must be planar, and must have 4n plus 2 pi electrons. Okay. And there are two more classes of compounds. Why? Because when we are discussing aromatic compounds, we must also mention about those. One is non-aromatic compounds, another is anti-aromatic compounds. So what are those compounds? For non-aromatic, the name itself implies that these are not aromatic due to reasons. So non-aromatic means which are not having this aromatic energy. Okay, and what are the criteria to not being aromatic rather than non-aromatic? It can be different. As I mentioned, there are three criteria to be aromatic: planar, cyclic, and 4n plus 2 electrons. So for non-aromatic, if one of these criteria get violated, then it will become non-aromatic. Like if a molecule is not planar, then it will become non-aromatic. Doesn't matter if it's a cyclic structure, it's having 4n plus 2 electrons, but if it's not planar, means it will not be aromatic, rather it will become non-aromatic. Okay? Same if it's some compound, it's not cyclic, okay, but it's planar, having 4n plus 2 electrons, then also it will become non-aromatic. Okay? So becoming aromatic is more difficult. You have to fulfill all these three criteria, then only become aromatic. If not fulfilling, then it's becoming non-aromatic. There is another special category, that is the anti-aromatic. Anti-aromatic is quite similar to aromatic, just violating one rule. So I'm going again and again these three rules: planar, cyclic, 4n plus 2 electrons. For anti-aromatic, it's obeying first two. It's planar, yes. It's cyclic, yes. But rather than having 4n plus 2 electrons, it's having only 4n electrons. Okay. If it's having 4n electrons, it becomes anti-aromatic. Okay. But to be anti-aromatic also, it must fulfill the other two: planar, cyclic, 4n. These three, then only anti-aromatic. If violating any of those, it automatically becomes non-aromatic. So the range for non-aromatic is really big. Aromatic and anti-aromatic, it's really have to follow these three. Only difference is aromatic 4n plus 2 and anti-aromatic 4n. Okay. So now we'll see few examples with different ring sizes. So let's start with three-membered ring. Here it's too small. I will go to slideshow, and then I will for the changing the slide, I will go to escape from here. So three examples are given here. Let's go for the first one, for cyclopropene. So cyclopropene, as you see, it's having only one double bond. That means there are 2 pi electrons, nicely matching with 4n plus 2 formula, where n equal to 0. It's cyclic, that is also fulfilling. But as you can see here, there is this sp3 carbon here. So that means that the delocalization is not really cyclic. Okay, and the delocalization, that the delocalization is interrupted. So it must be cyclic in the sense that sigma structure, of course, cyclic, but also the pi electrons must be delocalized in a cyclic framework. Okay, so if it's there is interaction between these, in between the structure, then it will not become aromatic. So that's why it's non-aromatic. It's because there is an interruption. If you just go to the other analog or other derivative of this three membered, so instead of a sp2 carbon here, if you imagine one cation here or cyclopropyl cation. So one in that case, what will happen? So one cation here means there is a free p orbital here, free p orbital here. Right? So now, once is a free orbital here, empty orbital, this guy, this pi electron here can really do the resonance. It can come here and make a double bond here, then it will be a cation here. And again, this can go there and make a double bond here, cation here. So that means there is a resonance hybrid. So these are the three structures. And these three, if you average out, is a dotted line means the double bond you see here, this structure double bond is possible here, double bond is here, double bond is here. That means the double bond and this positive charge is really moving around. So if we can draw a resonance structure here with a dotted line. That means the double bond, the probability of the double bond is everywhere, and also this cation can move around. Okay? So that means now in this structure you see is fulfilling all the properties or criteria to be aromatic. It's cyclic, and the resonance or the electrons are also delocalized in a cyclic pathway, and it's planar, and also it's having 4n plus 2 electrons where n equal to 0. So that's why it's a tiny, this is one of the smallest example of aromatic compound. So this cyclopropyl cation is an aromatic compound. And little change, if you just go to a, instead of positive, if you make a negative ion, it's a negative ion here, cyclopropyl anion. So again, there is a p orbital here. So in theoretically, it can also get delocalized. Okay, so it's a delocalized, and everything is a planar and everything. But if you now count the electrons here, negative charge means there are two electrons. Okay, there are two electrons because this is filled up with carbon. Negative charge means why I'm telling two electrons. Carbon was already having one electron, right? Elemental carbon. One electron means that's neutral. And you want to make a negative charge, that means from externally you have given another electron. Okay, that's why it's becoming negative charge. Or in other words, if you can theoretically think that from this structure means there are two CHs are there, carbon hydrogen bonds. If you deprotonate, you just take out one proton from here, just breaking one carbon hydrogen bond. So then also you can generate a negative charge, right? One proton H plus you are taking out, then only generate C minus, and C minus, the carbon hydrogen bond having two electrons, the bond, one bond means two electrons, both of this electron will go to carbon, then it will become negative charge. So that's why negative charge means two electrons. Okay, so here two electron, in double bond two electron, total four electrons, and 4n plus 2, if you formula, if you put there n equal to 1, that means it's having 4n electrons. And 4n electron cyclic structure, planar, it becomes anti-aromatic. That's why this is very unstable compound. This is anti-aromatic. Let's move to some other examples with different ring sizes. Let's go for 4-membered ring. Will be faster, little bit, we discuss a little bit faster. Cyclobutadiene here with two double bonds. Very simple. It's a planar structure, of course, nicely delocalized. You can draw all the resonance structure. But again here, 4n electrons, not 4n plus 2, 4n electrons. That means it's anti-aromatic. And one thing I must mention here, I forgot to mention, that definitely aromaticity with benzene, of course, definitely we have discussed that compared to cyclohexatriene, benzene is more stable by 36 kilocalorie per mole. That's the aromatic energy. That means we have already understood that aromatic means more stable. Non-aromatic means it's neutral. Non-aromatic, it's like a normal compound, neutral. But anti-aromatic means unstable, is higher in energy than the normal thing. Okay, so that's why when this cyclobutadiene having anti-aromatic property, it's really unstable. it's very difficult to generate. Even if you generate this one at very low temperature, it's a minus 78 degree, which is very low temperature where molecules supposed to be really freezed. Okay, but there also, if you once you make, it's immediately dimerized. Okay, so if you can see here, it's immediately dimerized. One of this double bond will react with another two and form this bond. This is strange molecule with three four membered rings, but still it will prefer to form this. Okay, this thing and form this compound, because by doing so, now you see this becoming a non-bonding non-aromatic compound. You see that is, it's like the cyclopropene, where the resonance get interrupted because of these are the sp3 carbons. Okay, sp3 sp3 sp3, these two are sp2 but not delocalized. That means this compound, the product here is non-aromatic, but this starting material here are anti-aromatic. So at very low temperature itself, because so unstable, because anti-aromatic is dimerized and then it will go to non-aromatic to get some stability. Okay, so that's why anti-aromatic compounds are so unstable and very reactive. Let's move forward. Just keeping the bond, this sigma structure the same ring size with the four membered ring. Previously we have seen cyclobutadiene. Now just removing one double bond, if we imagine dication. Okay, dication here, two times positive charge. That means cation means empty orbital, nothing else. So now this double bond can really move around, get delocalized here. Okay, it's planar, cyclic, and now you count the electron. Total only two electrons, because positive charge not contributing anything here. It's empty orbital only. Actual number of electron is only 2, which is giving nicely matching with 4n plus 2 formula, where n equal to 0, only 2 electrons. So 2 6 10, you remember this thing, 2 16 will give you the aromaticity. So here, although it's a dication which seems to be very unstable, but still it's more stable than its corresponding neutral compound, the cyclobutadiene. Okay, you can really generate this by just by doing this reaction with this antimony hexafluoride, just taking out this chlorine, and you can generate this, and it's stabilized it at low temperature, not like the other thing which also get dimerized at low temperature. Okay, you don't really need to remember this reaction, just to show you that this is possible to generate this kind of compound just by driving the benefit, or get just by utilizing the benefit of aromaticity. Other rings, let's move after 4 to 5. 5 here, the first example is very similar to this cyclopropene, where this get interrupted because of there is one sp2 carbon here in between. Although there's a diene here, but it can't really go cyclic. That's why it cannot get the aromaticity. So this is non-aromatic. Now if you make cation first, let's make a cation. So it's a positive charge here, that means an empty orbital. So now these double bonds can really move around. Then it's a cyclic structure and delocalized. But if you count the electron, 4 electrons. So 4 is the danger. 4, 8, 12, these are danger. 2, 6, 10 is good, aromatic. 4, 8, 12, these are the danger. It will give you anti-aromatic, provided you are fulfilling the other criteria of cyclic and planar things. Okay, so that's why this is very unstable. This is giving anti-aromatic compound. And for the other one, instead of making positive, you make a negative charge. And then if you see, if you count the electrons, other things are the same. Now it's fulfilling on 4n plus 2, because it's giving 6. 2 6 10 is good, so it's n equal to 1. It's almost like benzene, 6 electron, nicely delocalized, and is planar, so this will give you aromaticity. And now this aromaticity will really change nicely some properties of some compounds. You can really explain nicely from this aromaticity, like the pK of this compound. pK have you have learned, I guess Arindam sir taught you some amount of pK. pK for hydrocarbons, pK is quite high. That means the acidity of hydrocarbons, this is quite high. It's very acidity is very low. It's normally it's very reluctant to release any H plus, like methane, ethane, whatever. If you take those, getting methane, Me3 minus and H plus from methane is very difficult, right? But compared to this, if you take this hydrocarbon, this is also hydrocarbon, this guy here, cyclopentadiene, the pK is only 15, which is relatively quite acidic, surprisingly acidic. Why this is its pK is so low comparatively? This is because if it release a proton, then it will become a negative charge here. And once it becomes a negative charge here, then it can get delocalized and get aromatic property. So that's why, just to get the aromatic energy, it's release the proton much easily compared to other related compounds. Okay? And that's the benefit of aromatic energy. All right, let's move to 6 and 7 member ring. Benzene, we have already discussed, nothing to say much. It's of course aromatic. 4n plus 2 nicely is the perfect example. For 7 member ring, same here. When there is an interruption here, then it becomes non-aromatic. Here, in case of a positive charge, you just count electron, 6 electrons, aromatic. So that's why this, if you take the corresponding bromide here, is soluble in water. If you put in water, it will immediately ionize. It's like sodium bromide, if you sodium bromide or sodium chloride, that common salt we eat, you put in water, it will get dissolved, right? But that is so unusual for an aromatic compound. These aromatic bromides are quite stable and don't want to go to water. It's not soluble, rather it will prefer aromatic solvents. But surprisingly, this behaves like almost an ionic compound. You put in water, it will get ionized, this cation and Br minus, the bromide anion. And because once it becomes positive, it gets the aromatic energy. 6 electron, nicely delocalized and planar. And that's why it's preferred the positive charge here on this particular compound. This is another property you can explain just by aromaticity. So the last example of with the ring, and then here 8 membered with 4 double bonds, again 8 electrons is the danger, as you know. That means it's supposed to be anti-aromatic. But what happened, once it's a big ring, it gets some flexibility. Okay, it gets some flexibility. So that's why it's a big one. Rather be stay as a planar, it bends like a tub. It becomes tub, and once it becomes tub here, like this tub type kind of structure, the planarity goes. Planarity, there's no more planar, the low more planar. Okay, so in this structure it should supposed to be planar for 4 double bonds, but in reality this molecule bends and then make a tub, which is no more planar. What's the benefit here? If it's a planar molecule and having 4n electrons, this is supposed to be anti-aromatic. But if there is a possibility and flexibility is there, it becomes out of the plane, and once it's becoming non-planar, then from anti-aromatic it becomes non-aromatic. Of course, it's not possible that it get aromaticity because it's having 4 pi electrons, not 4n plus 2. But what it can do, just becoming bent, just by becoming bent, at least it get rid of anti-aromaticity, it becomes non-aromatic. Okay, so that's why this cyclooctatetraene, this is not a planar structure, it's like a tub like structure. And also these double bonds are not localized, which can be seen from this bond length. So carbon-carbon double bond length is actually 1.33, and this carbon-carbon single bond is 1.46. But in benzene, if you check the bond length of all these individual carbons, you will find only one type of bond length, no individual single bond, double bond length, only a average of this, because benzene is really delocalized. But in this particular compound, you will get two discrete bond length between carbon-carbon single bond and carbon-carbon double bond. Just give me 5 minutes. I'll be faster and discuss the thing very quickly, so that you can solve.
Sir,
Yes, yes,
sir, how this structure is not planar? Can you explain it again?
yes, sure. This is flexible. The structure with 8-membered ring, when it's a small ring, then it's there is not much flexibility that it can bend. But it's a 8-membered ring. 8-membered ring, it's flexible enough so that it goes to this tub shape. Tub. I don't have a model. Otherwise, I would have shown you with the model. If you make a model of this, you will see this is flexible enough. With 4-membered ring, it's not possible. So that's why cyclobutadiene is not possible that it will go out of plane. It must remain at plane and it will dimerize. Rather, but this molecule is flexible enough. So this bond and this bond, it will bend. It's a big molecule. It's planar like this. Okay, and then it's bent like this, and then become to this top shape. As I said, I am out of the campus this week, but next week I'll be there. I will make a short video, okay, with the model. It's a short video, and then I'll put in this YouTube playlist. Okay, so from the model you will see this. All right. Do you have a class now? Hello, guys. Do you have a class now? Or should I continue for 5 more minutes? Oh, okay. You have a class. Okay, so then what I will do, so let's have a class tomorrow also, but very short, 10-15 minutes. Because the assignment I have given you is really based on this last part, these things. If I wait till Friday, then it will be too late for you guys. Okay, so tomorrow we'll have a very short class, maybe 15-20 minutes, whatever. We'll see. 12 o'clock we'll start, and let's see how long it will go. And then I'll not add anything here. Whatever is there, 19 slides will remain on that. All right. So 12 noon tomorrow we'll meet again for a short class, and then discuss this thing, the remaining part, and then so that you can solve this assignment easily. All right. Okay, guys. Then I'll stop here, and see you tomorrow. Also, spread into your tell your friends, because at the beginning I said tomorrow there will be no class. Tell them that there will be a short class tomorrow, not a full class. Okay. Okay, guys. Thank you.